fresh water. Life cannot exist without it. It's not only the water we drink, it is a vital part of our daily existence. Yet this critical resource is increasingly becoming scarce. Nearly half of the global population is facing severe water shortages. Droughts are occurring frequently, affecting countless regions around the world, and not just the developing world. These alarming trends are also placing crop production and food production at risk, disrupting the lives of many communities, while water sources are persistently drying up. These issues are no longer limited to the Middle East and Africa. Water shortages affect several regions in the US, Caribbean islands, Southern Europe, Middle East, Africa, as well as Asia and many other coastal geographies. Considering the unlimited availability of seawater, it is not surprising that desalination was embraced globally as a logical complement to rivers and aquifers, which are increasingly disappearing around the world. In fact, seawater desalination has become the go-to freshwater supply alternative throughout the world and is expanding at a considerable rate. Over 20,000 desalination plants are currently operating around the world. These are essentially two desalination methods: thermal desalination and reverse osmosis. Thermal is the oldest form of desalination. As the name implies, heat is applied to the seawater to make it boil. The released steam is cooled, changing its state to liquid. But in the 1960s, reverse osmosis technology was developed and is now a de facto desalination industry standard. The major difference between the two methods is that reverse osmosis doesn't use heat and doesn't boil anything. Instead, the process applies tremendous pressure to force the seawater through a fine membrane to separate the saline and water molecules. Certainly more efficient than the thermal desalination method, but not without significant environmental and productivity implications. Just to name a few, firstly, continuous dumping of a highly concentrated saline solution back into the sea is destructive. Secondly, lots of energy is expended to maintain as much as 200 psi of pressure needed to force seawater through superfine membranes. And thirdly, maintenance, replacement, and disposal of membranes is costly and more intensive and disruptive. Let's explore these concerns in some further detail. A key characteristic of reverse osmosis is that half of the seawater that is ingested for desalination is returned back into the ocean with twice as much concentration of salt. Releasing huge amounts of hypersalty water or brine back into the ocean is dangerous because the impact on the marine life may be irreversible. Right now, the industry is producing over 37 billion gallons of brine per day. Nearly all of it is emptied back into the ocean. And because brine has a much higher salt concentration than regular seawater, it can wreak havoc on the plants and the marine life, which cannot be sustained. Moving on to the issue of membranes, reverse osmosis membrane is a complex multi-layered construct. Microscopic holes keep salt molecules from passing through to the freshwater chamber. Eventually, the accumulated salt particles render the membranes unusable, which warrants their frequent replacement, shell preparation, cleaning, and related maintenance activities. The frequency of membrane maintenance, replacement, and disposal are costly and labor-intensive. Finally, the energy required to operate reverse osmosis plants is significant, and considering the deployment scale of the reverse osmosis plants worldwide, this is both costly and environmentally unsound. Clearly, current desalination technologies are in many ways suboptimal, which allows us to introduce a new breakthrough desalination technology.